Hi everyone, this video is going to give you an introduction to factorial designs. Many experiments involve the study of the effect of two or more factors. So we are talking about factorial designs, which deals with effect of two or more factors. So in general, factorial designs are most efficient for this type of experiment. By factorial design, we mean that in each complete trial or replication of the experiment, all combinations of levels of the factors are investigated. So for example, if there are two factors, factor A, and it has two levels, A1, A2, let's say, or let's say it has A levels to make it more general. Okay, let me just make it a little bit more general. So I have level 1, this one has level 1, level 2, I'm going to call it, no, then I can't help that, sorry. Level 1, level 2 and level A, Ath level. So it has A levels, and then I have another factor, factor B, and then later you can generalize it for several factors, and that has level, so I'm going to call it K1, K2, KB. Each replicate contains all A-B treatment combinations. So then each replicate will contain all A-B treatment combinations. When factors are arranged in factorial designs, they are often said to be crossed. So a term that you will often see is crossed. The effect of factor is defined to be the change in response produced by change in the level of factor. This is frequently called main effect because it refers to the primary factor of interest in experiment. So for example, consider a simple experiment. Let's do it a little graphically. So let's say you have factor A, and this is on y-axis you have factor B. It is a two-factor factorial experiment. So this is a two-factor factorial experiment with both design factors at two levels. So there are two levels with both design factors at two levels. So you can think of it in real world. This could be factor A could be income, and you could have low income and high income. Factor B could be gender, male, female, right? Or it could be race, white, non-white, something like that, right? So this is how your factor is. This is just one example. It could have several levels and there could be several factors too, but this is the simplest form. So we are going to call these levels low, high, low, this is high, and low and high for this one too, low, high, right? The main effect of factor A in this two-level design can be thought of as the difference between the average response at the low level A and the average response at the high level of A, right? So this is, let's think of it like something like this. let's say this is 20, 40, 52, 30, right? So the main effect of factor A in this two-level design is the difference between is equal to difference between the average response at low level, response at low level of A and the average response at high level of A. So it would be average response at low level of A is 40, sorry, at high level would be 40 plus 52 divided by 2 minus 20 plus 30 divided by 2, which is 21. That is, increasing factor A from low level to high level causes an average response increase of 21 units. Sorry, this is 21, right? So verbally what it means is increasing factor A from the low level to the high level causes an average response in change or response increase in this case of 21 units. Similarly, the main effect of B is, so the main effect of B would be 30 plus 52 divided by 2 minus 20 plus 40 divided by 2, which is equal to 11. Now, if the factor appears at more than 2 levels, the above procedure must be modified because there are other ways to define effect of factor. So we'll discuss that later. So there's one more point that I wanted to discuss in this video, is that in some experiments we may find that the difference in response between the levels of one factor is not the same at all levels of other factors. So when this occurs, there is interaction between factors. So remember, let me use a different color. What is interaction? Because that is a very common thing in factorial experiments. When the difference in response between the levels of one factor is not the same at all levels of the other factor. This is what is called interaction. So the first one, the previous example, the idea could be illustrated graphically. So I'm going to plot the response data in figure that we plotted earlier. So let me just do that figure again so that they're both together on the same screen. So this one was our low high for B, and I'm just going to write in shorthand low high for factor A, right? And these are, this was 30, this was 52, 20 and 40, right? So the plot of this, if I plot the response data for this figure, this is how it's going against factor A for both levels of factor B. So this is the plot. This plots the response data in, let's call it figure 1. Against factor A for both levels of factor B. So this is my factor A, and this is the values of response. This is my minus of and plus level, low and high level of factor A. So at low level of factor A, let's say this is 10, 20, 30. Here, this is my B minus, right? When I have minus, the B minus is 20. Then when I have plus, my B minus is, so I'm going to, at plus, my B minus is 40. So the 30, this one is my 40. This is my B minus, right? 20 and for plus, B minus is 40. Now when factor A is minus, that is low, that is there, and then I have B plus is 30. So it's here. That's my B plus, and when factor is high, it's 52. So 30, 40, 50. Somewhere here. 52. So you see, the lines are approximately parallel. Parallel lines indicating lack of interaction between factors A and B. Lack of interaction. So I can do another two-factor factorial experiment, but this time I'm going to show you that it has interaction. So this was the example that we discussed is an example where there is not much interaction. Maybe there is some, we don't know, like if we expand it, but the fact that these lines are almost parallel indicates lack of interaction. Now the same thing, like two-factor experiment again, both the factors are low and high, right? So let me use a different color. So this time again I have factor A low and high, factor B low and high, right? So my factor A low is 20 and B there is 50. And then this one is 40 and 12, let's say. So like in the previous example, we can calculate the average response increase when increase factor A from low to high level, or for factor B also, like we did in previous. So I'll leave that for you to do. I just want to show that there in this one you can see that there is some interaction. So this is factor A, low, high, and this is my response. So here I'm going to plot the response data. Okay, so when factor A is low, B minus is 20. So let's say this is 10, 20, 30, 40, 50. That's how far it's going. Let's say 60. So B, A, and then B minus is 20. And then when factor is positive, B minus is 50. So I'm going all the way here, right? So this is my line now. B minus, B minus. Then when, so this is my 20 and this is 50. When factor A is positive, B plus is 40 and 12, right? So 20 and 50. Now we have 40 and 12. So where is my 40? 40 is somewhere here. And 12 is somewhere here. Let's see. Sorry. That's B plus 40 and 12. So this is an example of factorial experiment with interaction. Because the lines are intersecting, it indicates an interaction between factor A and B. So two-factor interpretation graphs such as these are frequently very useful in interpreting significant interaction and in reporting results to non-statistically trained personnel. However, they should not be utilized as sole technique of data analysis because the interpretation is subjective and the appearance is often misleading. So there is another way to illustrate this concept of interaction. If you were in regression world, suppose both of your design factors are quantitative. So if both design factors are quantitative, you can just use the regression technique to figure out the significance of interaction, statistical significance of interaction. So if both design factors are quantitative, right, you don't need to use the effects model or ANOVA approach. Quantitative, I need one more TIVE. For example, let's say temperature, pressure, time, etc. Then a regression model you can use a regression model. Of the two-factor factorial experiment could be written as y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 or beta 1 2 we usually call it x1 x2 plus error term, where y is response, betas are the parameters whose values are determined by x1 variable that represents factor A, x2 variable which represents factor B, and x1, x2 represents the interaction. This is interaction between A and B. And then you can just go on with your analysis just as you would in regression. Interaction is actually a form of curvature that appears in the response surface. So if you think of it geometrically, or if you do a contour plot, that's what you see. A significant interaction will often mask the significance of main effects. So it's very important that you consider that. When the interaction is large, the corresponding main effects have little practical meaning. And we are tempted to conclude that there is no effect due to those factors. However, when you examine the effect of A at different levels of factor B, you see that that's not the case. For example, factor A has an effect, but it depends on the level of factor B. That is, the knowledge of A-B interaction is more useful than knowledge of main effect A. So remember, a significant interaction will often mask the significance of main effects, and that is why it is very important that you explore the interaction effect whenever you have more than one factor. So remember, in summary, the factorial designs have several advantages. They are more efficient than one factor at a time. Furthermore, a factorial design is necessary when interactions may be present to avoid misleading conclusions. And finally, a factorial design allows the effect of a factor to be estimated at several levels of other factors, yielding conclusions that are valid over a range of experimental conditions. So this video has already gone too far. I will make a short video where I will give you a real life example of two-factor factorial design, and we will write down the effect model for the same.